We're going to use the Huffman encoding to encode this word, Ada Lovelace, one of our famous computer scientists. So a Huffman code compresses a data file. So we're going to look at this piece of text to do that. Now, if we were going to just store this normally, just using ASCII, I would count the letters or the characters. So 1, 2, 3, include the space, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 characters times 7 bits equals 84 bits. So if we were going to store this just using ASCII, just as it is, it would take up 84 bits. But when I encode this using the Huffman code, it's going to use a lot less data than that. Now, the first thing that you have to do is figure out the frequency of the letters and the spaces that are used. So the best way to do this is just to have the alphabet there, including a space as well. I've only done this using capital letters, not lowercase, because I don't want to complicate it too much. So we've got here A, and then a D, and then an A, and then a space, and then an L, O, B, E, L, A, C, E. So now we've done our little tallies, we can actually write at the top, well, that's 3, 1, 1, 2, 2, 1, 1, 1. Huffman trees always begin at the bottom and work their way up to the top. And you have to be quite careful to make sure that you're creating your branches of your trees going left to right. So it's quite obvious, otherwise you're going to get a bit confused later on. So we always start with the lower frequency letters first. So that's a high frequency one because that one's got 3. But C and D are low frequency because they only appear once each. So I'm going to put those first on my tree. So I'm going to go C, D, and their frequencies added together makes 2, because 1 add 1 is 2. So once I've done those, I can cross them off. Moving along, these are high, but those 2 are low. Those both are 1 as well. So I'm going to put those 2 on there as well. So O and V, and their frequencies added together make 2. So I'm going to cross those off now as well. Now the only one left with a frequency of 1 is the space, so I'm going to have to join that up with one with a higher frequency. So if I just go for the L, because that's the closest one to it, I then need to do 3, because their frequencies added together makes 3. And I can put the space on that side and the L on that side, and I can cross those off my list. And then we've just got the A and the E left. E has the lowest frequency out of those 2, so I'm going to figure out where to put E next. So I've got to try and do some guesswork here. I'm going to put it here because that's also a low frequency. And it now makes 4. So E is 2. And that's that one. But then branching off that is 2. So the higher up the nodes go, you're adding the cumulative amount. So C appears once. D appears once, so that makes 2. E appears twice, so that makes 4, which is placed there. So I've done that one, and I'm just left with A now. A is 3, so I've just got to figure out where to put that. Before I do that, I'm going to join these 2 together. So that makes 5. So where am I going to put my A? I'm going to go for this side because it's a lower number, and I'm going to add 3 and 5 3 and 4, sorry, together to make 7, and then my 3 is my A, and then I've just got my main branch left, and that makes 12. And if you see, I've tried really hard to keep the branches going left and right as I've drawn this. Also, I've made sure that the higher frequency letters are towards the top, which they are, and the lower frequency letters are near the bottom. That is the key. So that part of it is probably the most complicated part. The next bit is slightly easier. So if I branch left, then I want to be using a 0. And if I branch right, I want to be using a 1. So that's the binary digits 0 and 1. So now I just need to follow the path and just record the path that I'm taking on this tree to get to that letter. So I've gone left, right, so I go 0, 1. I've gone left, left, right, so I go 0, 0, 1. Left, 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 0, 0, 0, 0, left, 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 right, 0, 0, 0, 1, right, 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 1, 1, 1, right, right, left is 1, 1, 0, right, left, left is 1, 0, 0, right, left, right is 1, 0, 1. So now I've given each character its own unique code. So if I was going to write Ada Lovelace again now, but using my encoded binary digits, I would do it like this. So the A is 0, 1. The D is 0, 0, 0, 1. The A is 0, 1, and I'm going to forward this for you. So that's all of the letters now encoded into binary. So if we count up all these bits now, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So when we've encoded it using the Huffman code, it has only taken up 35 bits compared to the 84 bits. So you can see why the Huffman code would be useful, especially if you've got a massive piece of text to encode. If you do a quick Google search for Huffman tree generator, you'll find this website, and it just allows you to type in your words just so that you can check whether you've got your Huffman trees right. Now, the Huffman trees that it produces will look slightly different to the ones that you've done, and that's because the letters might have been taken in a slightly different order. But what you can check is the actual number of bits that have been created using the Huffman encoding, and match that with yours to check that you've done it right. So if I just add these all up, it's got the letter and then it's got the frequency next to it. So if I've got 2 bits in there and a 2 there, I know that I've got to do 2 times 2, which is 4. So then I've got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So mine was 35 bits, this is 35 bits. So we can be pretty confident that we've got our Huffman trees right.